All right. Well, thank you very much. So I just wanted to give, basically in this talk, insights into the HDTN's implementation of LTP. This won't cover benchmarks per se, but if you're interested in that, Fred Templin's going to be giving a talk on that tomorrow, so go see his talk if you're interested in benchmarking. So with regard to the implementation of LTP as it's written in HDTN, we took a asynchronous design, and asynchronous essentially means it's going to be callback function based. If you're familiar with JavaScript, you're going to write a lot of callback functions. You're going to get big into asynchronous programming. So that's the approach we took. It's going to be in C++. It's written using the Boost ASIO libraries, and so hence it's going to be cross-platform. So when you write it in Boost, you're going to get the operating system functions that do asynchronous are going to be called automatically, whether it's using epoll on Linux or KQ on BSD or overlapped IO on Windows. And so we used a lot of the Boost ASIO objects, everything from sockets to timers to resolvers to object handles to stream descriptors, etc. We use a lot of the functionality there. This slide gives a general overview of the LTP over UDP architecture. And so I kind of divided it up into threads. So at the top, that blue box, you see one thread that is going to manage the socket. So we have one thread per bound UDP port. The way LTP over UDP is essentially written is the specification says that you should use UDP port 1113 and bind it there, and all communication goes over that. So we have one dedicated thread dedicated to managing that UDP socket. And so its job is to ingest all these packets as fast as possible. You see on the left there, we're doing socket reads. We're going to look at the first couple SDNVs, or self-delimiting numerical values, decode them. If your CPU supports it, it's going to do an AVX 256 decode of those. And then it's going to be able to look up which session that UDP packet belongs to, and it's going to pass it over to the engine ID, the receiver or the sender whom that packet belongs to, and it's going to swap it into its circular buffer. We're trying to avoid UDP packet drops because of lack of processing time. So that top thread is trying to give those packets and tell these other threads to process. So you see two other threads in this example at the bottom there. On the left, you see a receiver. On the right, you see a sender. The receiver, these threads are processing these packets. They're running asynchronous deadline timers. They're calling red part reception callbacks. The sender's calling transmission requests. So all these are using doing asynchronous IO within those threads there. One way, I think, one way to really kind of wrap your mind around on this asynchronous idea is taking a look at how we test out our implementation and our regression testing. So the way we test out our implementation of LTP, we set up an LTP engine that's a sender. You see that on the blue on the left, and then a receiver on the right. Now, rather than connect them directly together, what we do is we have a utility process that's built in, that we have as a utility in HDTN called our UDP delay simulator, acting sort of like a proxy or a middleman. And it's going to intercept these packets, and it's going to apply a delay that you specify to these packets, similar to how you would LTP would be in real life. But it also gives you the ability on those that delay simulator to bind a callback function to it, so that every time a UDP packet is received, it can call a custom callback that you specify onto whether or not you want to drop the packet or not. So in that custom callback, you'll get the UDP packet received. And in this example, what we're doing is we're going to take that UDP packet, look at the first byte, and that's going to tell us what type of LTP segment it is. And in this example, let's say I want to drop all report acknowledgement segments. So what we're going to do is we're just going to, the function's going to look at it and see, is it a report ACK? If it is, we're going to return true, and our UDP delay sim is going to drop that packet. You can do all sorts of fancy things with this, such as rearrange packets and all that, but for this example, we're going to keep it simple. And so the next thing that's going to happen is in our framework, testing framework, we're going to start a transmission request on the UDP sender. And basically, we're going to, in this example, we're going to give it a fully read data, which is fully reliable data to the sender, and say, hey, send this to the receiver, that the sender is going to take ownership of the transmission request and the memory associated with it. And the next thing that's going to happen is that the sender engine is going to call a custom callback function that we've created within our unit test framework called the transmission session completed callback, meaning, hey, I sent the data out, here's a callback per the LTP specification. And in this case, all we're doing is we're incrementing a counter within our testing framework, number of callbacks there, as you see highlighted there. Next thing that's going to happen is the receiver is going to call a callback function called the red part reception callback. That's another callback that's specified, called out in the LTP specification. And what are we going to do? We're going to increment another counter, number of red part reception callbacks. Now, what's going to happen is the receiver is going to send reports back to the sender. And then with LTP then is LTP says, okay, the sender received the report. Now it's got to send a report acknowledgement back to the receiver. So the receiver knows that it got its report. However, we're dropping all those report acknowledgements there. So the receiver is going to call a second custom callback function called a reception session canceled callback. The receiver is assuming, hey, the sender did not get my reports. Therefore, I'm going to notify the user that we have a canceled session here. So we're going to increment another counter here. And then within our framework, we're going to, in order to check our assertions, we're going to first wait for these expected counters to increment. And once that happens, we can then check a bunch of assertions. I'm not going to run through all of these for the sake of time, but standard assertions that you would write in a framework. Another thing I want to talk about in this presentation is some optimizations that we did with our LTP implementation. One thing that I'd like to look at is that we looked into and found very beneficial is the idea of custom allocators. So what I'm getting at is in blue there, the blue box on the left, that is a hash map that is currently being used in our implementation. In C++, it's also called an unordered map. If you're familiar with hash maps or unordered maps, they hash things and stick your data in buckets. And so what happens? We want to send a new bundle, so we want to create a new LTP session, and so that new session is added, given a session number as a key to that hash map, and that data gets popped into a bucket, or whatever. And we're going to call that container data. The orange there we see is container data. So how does it get that memory? Well, the map has, every map has what's called a default allocator associated with it. And that basically says, if I need new memory, I'm going to use operator new or malloc. I'm going to call the OS memory manager, and I'm going to get new data from the operating system. What we did was we took that default allocator and we replaced that with a linked list allocator that's going to recycle memory instead of relying on the operating system new and delete all the time. So that container data in orange now becomes in C, if you're familiar with a union, this data now becomes a union. So when it's owned by the map, it's still container data, but when it's owned by the new custom linked list allocator, it now becomes a singly linked list. So hence node star next there, a pointer to the next data. So let's say now we create a new LTP session and it's going to get hashed to bucket 2. Our new allocator can pop that top node off and throw it into bucket 2. And now we just bypassed new and delete, and we're recycling memory at this point and saving a lot of those expensive operating system calls. Another optimization, we want to strive to prevent copying memory as much as we can. And one of the concepts there is when you create a new UDP packet, you don't have to get all your data and construct the whole UDP packet into contiguous memory where all the memory is sequential. What you can do is you can tell your socket that you, and the Boost ASIO library supports this, is what you can do is given an array of these pointer length pairs. So in this case, if we want to send a new data segment, a piece of red data, what we can do is we can create we want to send a new LTP data segment, which consists of a few bytes of what's called an LTP data segment header, and then we have the actual red data itself. So we don't have to go and recopy our LTP red data into a piece of contiguous memory. We can give it some pointer length pairs and say, here's socket, here's the pointer to this header, now here's the pointer to this data, create the UDP packet and send it. So hardware acceleration and fancy instructions available on x86. One thing that we looked at a lot is how can we do branchless SDNV encoding and decoding operations. So an LTP packet is made up of these self-delimiting numerical values, and essentially can essentially take 10 bytes to represent a 64-bit value up to 10 bytes. So one thing we did was implement some branchless SDNV encoding and decoding operations within HDTN. And then what our build system will do, we use CMake to build it. And by default, what it'll do is it will look, when you're going to compile LTP, is it will test your processor and see, hey, do you have these flags that can support these fancy SIMD instructions? And if you do, then it'll also test your compiler and see that it can compile them as well. And if it can, it will by default try to use those. We also look and see if you have the RD seed instruction. The LTP specification says it's important to use true random numbers. And so as an extra source of randomness, it can utilize the RD seed instruction available on modern Intel processors. So I just talked about optimizations. Now, what about some non-standard features? How can we make LTP better outside of the specification laid out? Well, one thing you may know is that some networks induce what are called out-of-order packets. You send these UDP packets out, they arrive out of order at the receiver. And that can be a problem with LTP. And I'm going to thank you to Brian Cepos for pointing this out with these networks that can tend to do this. And so essentially what we want to do is out-of-order packets can be a problem with LTP because it could get a packet, a last checkpoint packet, and says, oh, there's some gaps that we must have lost some data. Rather than assuming that they were dropped, it will by default try to tell the sender right away, hey, there's going to be gaps here. But with out-of-order packets, those gaps weren't really lost. They're just coming a millisecond later after you process that next packet. And so you could prematurely tell your sender that you've lost data when really you haven't. So one thing we implemented, so at the receiver, we can defer a synchronous reception report, or if there's out of order data segments, and that's going to minimize your total report segments sent. You're going to have the smallest reception claim size. And at the sender, we can defer data retransmission when report segments come in out of order. Now, these are like very small delays that you can user can kind of specify in their LTP configuration, and you can also change it at runtime. But we're talking maybe a few millisecond delays that you can add in to say, hey, just wait a few milliseconds before you send that report segment out, and let's see if we can see if there's some packets coming in out of order, and then we can minimize retransmission in networks that induce out of order packets. One thing, a feature that our team has grown to love is this, we came up with, is called LTP ping. I see Bill smiling there. So what we do in this, and I wouldn't say we're exploiting a loophole in the LTP specification, but in a sense we kind of are. What we do is that what the LTP sender is going to do, if it wants to know that the link is really there or not physically, it will send a cancel segment of a known non-existent session number to the receiver. And per LTP specification, the receiver must respond whether or not that session existed or not with a cancel acknowledgement segment. And hence, the sender can determine if the link is actually active during times of no data segment being sent activity, no bundles being sent, or and so a user-specified link down callback will be called if that cancel act is not received after the max retries times your round trip time. So that's a feature that we've grown to love and rely on quite a bit in our testing. We can get we've noticed we can get some pseudo flow control within HDTN and bundle protocol. And what that means is, so with our implementation of LTP, our LTP receiver won't send that synchronous or that reception report until after the user's custom red part reception callback completes. Like, here's the full data, but I'm not going to let the receiver know until that callback completes. And likewise, our sender is going to block new transmission requests when there's max sessions or max total bytes in flight. These sessions have not been closed out. So you can essentially achieve like a pseudo flow control by that receiver blocking or doing actual processing within that red part reception callback, not to exceed the margin time. So essentially the receiver is going to sort of slow down that sender. There's an experimental feature called LTP sessions on a solid state disk. You may have heard in the earlier talks this morning about the long Mars delays. If you have high rate data over extremely long delays, you can get where you require a terabyte of physical memory to keep all that session data. So what we have is the ability to store that data, LTP session, into files created every couple seconds, and it will stash all that session data on those files on the disk. And once those all that session data for that file is closed out, that file will be deleted. And this adds no extra threads involved. It's just an extra asynchronous I/O call using the Boost ASIO library. So we've tested that a little bit, but we haven't fully hashed it out. And real quick, we have class inheritance, so you can write other LTP convergence layers that don't use UDP. We did one over IPC interprocess communication or shared memory for the purpose of benchmarking and defined the max theoretical rate of the LTP processes bypassing the OS and UDP. We wrote another one for NCAP where you could intercept LTP NCAP packets if you want to avoid the whole UDP stack, and maybe you want to interface that with a radio API instead of using UDP. And then finally, you can pretty easily use our LTP implementation as a library, just a few pieces of CMake script in your project. You can import it and as a library. With that, I want to stop it here for time, and that's all.
Thank you. I want to take maybe 1 or 2 minutes for a couple of quick questions and then go on our last talk.
Ryan, I don't remember if it was you or one of your colleagues that said that you send multi-message.
Yep. Yeah.
How does that work? Do you have multiple segments available that you put into the send message at one point in time, or do you have to wait for them to arrive?
We support the send M message, not at the receiver level, but at the sending level. And you specify that in your configuration. If you want to send more than one UDP packet at a time, what it will do is we've made a custom asynchronous send M message. On Windows, it's called transmit packets. But basically what it does is it sets that send M message. It uses that send M message call, but it puts the socket into what's called non-blocking mode and then calls an async wait on it. And while it's doing an async wait, it can go service timers that expired and process other things. So yeah, we do have a fully asynchronous send M message being used within the implementation there. Yes. And so that'd be cool to actually test that out and benchmark that too at some point. Yes, in the back.
Space for that last experiment you just talked about, where writing outbound data.
Yeah, for the writing convergence layers is outside of UDP. Yeah. Or sorry, the last one. Oh, yeah. This one?
Like memory?
Yeah, yeah. So it's especially with space applications, it could be hard to have a terabyte of physical memory, especially in space. And you could essentially, if you don't have that memory, you could slap a terabyte solid state drive and run off your sessions off of that instead of needing a terabyte of memory for these really long, like 1 minute delay, multi-minute delays with gigabit rates, things like that. That's where you would want to use something like this. And so it's doing asynchronous file I/O. Essentially, it's sort of like fwrite, fread, those, except it's doing them asynchronously with boost.
Like a persistent benefit. Like
You, right, yeah. It's highly experimental at the moment, so it's not necessarily guaranteed if you pull the plug on it that it's going to restore those sessions yet, but it was more of a proof of concept. How do we handle these extremely long delays, which is going to be important. Yeah.
And I think she cut it off right there and move on to the last topic.
Yep.